hope you can hear and see me clearly.
Yes, to both topics.
Perfect. Okay, so let's start. Yeah, I want to show you something about our production logistics framework for the SYNTECS process and machine, which is a simulation-based industrializability check of SYNTECS. The main objectives for us were mainly two questions. So how does a production system change when a new technology like the SYNTECS machine is introduced, and what does it mean for capacities, material flows, and logistical targets? And the scope, as mentioned before, is the industrial use case by ETL for the vapor chamber production. And we took a two-level approach, where we first start with a generic assessment of the production system, like capacity checking, floor space calculation, logistics planning, and more in detail then, after this step, we took the material flow simulation, which should be the focus of my presentation today. So let's see. Let's start with some assumptions we made. The SYNTECS machine should replace the sintering process for the vapor chamber production, and therefore the first idea was to match the cycle time of that machine and take the number of machines equivalent for SYNTECS, and we came there up to a requirement of about 14 machines. In the picture right, you can see a screenshot of the simulation model. In green highlighted, you can see the SYNTECS machines. So we have 7 machines for the top plate and 7 machines for the bottom plate. And the processes that should be replaced by SYNTECS are, beside the sintering, the powder filling, pressing, punching, and the resistance welding. So that we have about 8 machines which were replaced by the 14 machines from 14 SYNTECS machines. Then you need to look on what parameters are relevant, what parameters can we change in a production system, and therefore we focused on the availability of the machine, the process time, the buffer capacity, and the mean time to repair if you have kind of failure. For the performance measurement, we took some KPIs from the production logistics target system by Wiendal 2008, which focused, for example, on the throughput time, utilization, work in progress, inventory, and the output. And due to the small parts and larger lot sizes for the logistics, we have not that much, not a high transport frequency, so we focus more on the overall system performance during our optimization. So before we can do our simulation study, we need to do some preparations for our experiment plan. There we used kind of a 2K factor design, which goal is to analyze the sensitivity of KPIs regarding the parameters we change in the simulation model, and therefore we define min and max values for each parameter and simulated a few combinations to check what is the influence of one parameter to our KPI. For example, you can say the availability has a medium influence, as you can see here on the output. The process time has a higher influence, and mean time to repair, for example, has a small influence on the KPI. So that's a qualitative visualization here. We have clear data in the background for it, but for that, I think it's fine. After we've done that, we did our experiment plan. So due to computation time, the number of simulation runs must be well chosen. So we need to define a mesh of parameter sets with min and max values and a step size for each parameter. And so here our previous analyses are relevant to decrease the number of simulation runs. So we started from larger step sizes to smaller step sizes for the interesting areas we found out, and in the final setting we took about 1,100 scenarios and 2,200 runs in a runtime about 10 hours. So we have our parameterizable model, our simulation studies with the several parameters, and as an output, we have our results as an Excel file, for example, which you can use for further analyzations. So now let's have a look into the model. I just want to show you some little effects you can analyze. So I need to share the model. I hope you can see it right here.
Yes.
So we have here our simulation model. In the previous part, you have all the steps before the syntax machine will come. Here, the green ones, as I mentioned before, are the syntax machine. And here you have the in dark blue, the diffusion bonding, which is the step where the top and bottom plates are welded together. And now I start with run scenario where we use a syntax machine. And in this case, the syntax process, for example, is a bottleneck. I can speed up the simulation. As you can see, the buffers before the syntax process is running full, and our parts are produced here in the back. And in this area, after the syntax process, you have no increasing buffers. The diffusion bonding machine, for example, is not all machines have a high utilization. And if we now, for example, change the process time from, for example, that is 30 minutes by half, we, for example, take 15 minutes per half and restart our simulation model right now, then we can see, okay, the buffers are running full, and now the machines here are completely working, and the buffer is running full right here. So the bottleneck switched from the syntax process to the diffusion bonding, and so we need to find optimized parameter setting where the system is quite well balanced. Now you can see all buffers are running full, and that is has a bad influence on other KPIs. So that's from now. I get back to the presentation again. So now we run that few thousand simulation scenarios. What shall we do now? So we have a few KPIs which may have a different weight. For example, the output value is more relevant than the utilization of machines or the work in progress inventory. So we defined an evaluation function for the optimization, which based on a normalized values and a weighted factor between 0 and 1. And what you can see on the right side here is a scatter plot for one specific scenario. As you could imagine, it's a multi-dimensional optimization problem. So we fixed the buffer size in that scenario and the mean time to repair to 10 minutes and a specific weight scenario. And what you can see here is, for example, you can have, if you have a high process time for the syntax machine, the weighted sum is quite low. And if you decrease the process time, you get something like a peak maximum front for our weighted sum. So in this area, the syntax machine is the bottleneck. And if you go farther to the left, so you decrease the process time, and the values are the weighted sum is going low. So you can decrease the process time, but in this parameter setting, it's not necessary. Even though the buffers are getting full, and so our overall parameter set is not that good then at the process time of about 20 minutes per part or per half, or 40 minutes for the whole vapor chamber. So just a quick introduction into that. So our main takeaways from our work package were, okay, for this use case, 4 machine types can be replaced by the syntax machine. for the vapor chamber production. For the top and bottom vapor chamber halves, we have 8 machines, which must be replaced by minimum 14 SYNTECS machines, based on the process time of around 40 minutes per vapor chamber. To match the bottleneck, of course, you can say if we have a better process time, you can go lower with the machine number to, for example, 11 to 12 machines at 30 minutes per vapor chamber, or which maybe more the current status is that we have, for example, 60 minutes per vapor chamber, and then we get to 20 machines. So we found out that the logistics are not the main bottleneck for the industrialization of the SYNTECS machine in this use case due to the small amount of transport. What we can say is due to the long process times compared to sintering, we have a high number of machines which is maybe less economically, and but because of the high number of machines, the influence on of failures is quite reduced because it's more balanced. So that's all from my side. If there are any questions, feel free to ask. And thanks for your attention.
Thank you, Niels. Let's see if there is any question I can do. I have one question that is basically if you had more things to test, or at least to predict using your simulation model, what could be these additional things to do or to be done? So which could be the next steps in terms of the work that you have done? If there is something that could be additionally be done, or actually it's not.
Of course. So if of course it depends on the use case, but we definitely could go more into detail regarding some failure profiles, or if you have a use case with more complex logistics, you can you can model all these parts as well and check what influence that case would have. So there's definitely a lot of things you can go more deeper into, especially for the optimization. You can test several algorithms to check if there are more other local optimums, and so I think it always depends on the use case and the data you have.
Mm-hmm. Okay. And during this simulation and the work that you've been done in the project, if you have in mind which aspects were more difficult to integrate in your simulation model, do you have any aspect that you might identify?
So of course it's always about getting, so from the simulation perspective, it's always you want a lot of data, it's also you want more data than you get, of course, so it's the challenge to get enough data to get a good base for some results to extract, but it's a typical conflict, from our perspective. So I think that's definitely the most interesting and difficult point here.
Understood. Clear. Thank you, Niels.